Hi class, how are you today? That's normal. The learning target for today is to be able to find the area under a standard normal curve. You're a 3 if you can find the area under a standard normal curve. You're a 2 if you can convert raw stores to z-stores and vice versa. You're a 1 if you can convert raw stores to z-stores or vice versa. Or you're a 0 if you cannot convert raw stores to z-stores or vice versa. Let's get started. Section 6.2, Standard Units and Areas under the Standard Normal Distribution. I wonder what the letters on his shirt says. Can anyone figure that out? Alright, so the focus points for this lesson. Given mu and sigma, convert raw data to z-stores, and vice versa. Given mu and sigma, convert z-stores to raw data. And graph the standard normal distribution and find areas under the standard normal curve. Z-stores and raw stores. Normal distributions vary from one another in two ways. The mean mu may be located anywhere on the x-axis, and the bell shape may be more or less spread according to the size of the standard deviation sigma. The differences among the normal distributions cause difficulties when we try to compute the area under the curve in a specific interval of x values, and hence the probability that a measurement will fall into that interval. It would be a futile task to try to set up a table of areas under the normal curve for each different mu and sigma combination. We need a way to standardize the distribution so that we can use one table of areas for all normal distributions. We achieve this standardization by considering how many standard deviations a measurement lies from the mean. In this way, we can compare a value in one normal distribution with a value in another different normal distribution. The next situation shows how this is done. So what we're doing here is just comparing it by how many standard deviations. So not based on actual numbers, but based on these standard deviation, how many standard deviations a measurement lies from the mean. Suppose Tina and Jack are in two different sections of the same course. Each section is quite large, and the scores on the midterm exams of each section follow a normal distribution. In Tina's section, the average was 64 and her score was 74. In Jack's section, the mean was 72 and his score was 82. Both Tina and Jack were pleased that their scores were each 10 points above the average of each respective section. However, the fact that each was 10 points above the average does not really tell us how each did with respect to the other students in the section. In this figure, we see the normal distribution of grades for each section. So notice that Jack's section is much more spread out, while Tina's section is much more skinny. All of it's in a smaller area. So what you can determine from this is that Tina's grade is actually much better compared to the rest of the students in her class. It's a harder probability, a lower probability for her to get that 74 because there's so little bit of room in this area, but there's a lot of room from the 82 onward. Tina's 74 was higher than most of the other scores in her section, while Jack's 82 is only an upper middle score in his section. Tina's score is far better with respect to her class than Jack's score is with respect to his class. The preceding situation demonstrates that it is not sufficient to know the difference between a measurement and the mean of a distribution. We need also to consider the spread of the curve or the standard deviation. What we really want to know is the number of standard deviations between a measurement and the mean, This distance takes both mu and sigma into account. We can use a simple formula to compute the number of z and standard deviations between a measurement x and the mean mu of a normal distribution with standard deviation sigma. So the number of standard deviations between the measurement and the mean is equal to the difference between the measurement and the mean divided by the standard deviation. A way to write it is that z is equal to x minus mu over sigma. So the difference between the measurement and the mean divided by the standard deviation. The mean is a special value of a distribution. Let's see what happens when we convert x equals mu to a z value. Well, if you do mu minus mu, any number subtract itself, it's 0. 0 divided by sigma is 0. The mean of the original distribution is always 0 in standard units. This makes sense because the mean is 0 standard variations from itself. An x value in the original distribution that is above the mean, mu, has a corresponding z value that is positive. Again, this makes sense because a measurement above the mean would be a positive number of standard deviations from the mean. Likewise, an x value below the mean has a negative z value. So if it's equal, z is 0. If x is greater than the mean, the z is positive. If x is less than the mean, z is negative. A pizza parlor franchise specifies that the average amount of cheese on a large pizza should be 8 ounces and the standard deviation only half an ounce. An inspector picks out a large pizza at random in one of the pizza parlors and finds that it is made with 6.9 ounces of cheese. Assume that the amount of cheese on a pizza follows a normal distribution. If the amount of cheese is below the mean by more than 3 standard deviations, the parlor will be in danger of losing its franchise. How many standard deviations from the mean is 6.9? Is the pizza parlor in danger of losing its franchise? Since we want to know the number of standard deviations from the mean, we want to convert 6.9 to standard z units. So we do 6.9 minus mu, which is 8, and divide by the standard deviation, 0.5. And that comes out to negative 2.20. So that means the pizza parlor is not in danger of losing its franchise. It's pretty low, but not low enough to be dangerous. Given an x distribution with a mean mu and a standard deviation sigma, the raw store corresponding to a z-store is x equals z times sigma plus mu. So this is a way you can get the raw store from the z-store. Before we were doing the z-store from the raw store. So both of these are important. Standard normal distribution. If the original distribution of x values is normal, then the corresponding z values have a normal distribution as well. The z distribution has a mean of 0 and a standard deviation of 1. The normal curve with these properties has a special name. The standard normal distribution is a normal distribution with mean mu equals 0 and a standard deviation sigma equals 1. Any normal distribution of x values can be converted to the standard normal distribution by converting all x values to their corresponding z values. The resulting standard distribution will always have mean mu equals 0 and standard deviation sigma equals 1. So you can turn any normal distribution into a standard one just by converting your raw stores, the x, into z-stores. Areas under the standard normal curve. We have seen how to convert any normal distribution to the standard normal distribution. We can change any x value to a z value and back again. But what is the advantage of all this work? The advantage is that there are extensive tables that show the area under the standard normal curve for almost any interval along the z-axis. The areas are important because each area is equal to the probability that the measurement of an item selected at random falls in this interval. Thus, the standard normal distribution can be a tremendously helpful tool because it will help us find the percentages of things. So we turn everything into z-scores, and then we can use it to find percentages, probabilities of things, using a standard normal distribution table. Using a table to find areas and probabilities associated with the standard normal distribution is fairly straightforward activity. However, it is important to first observe the range of z-values for which areas are given. This range is usually depicted in a picture that accompanies the table. In this text, we will use the left tail style table. This style table gives cumulative areas to the left of a specified z. Determining other areas under the curve utilizes the fact that the area under the entire curve is 1. Taking advantage of the symmetry of the normal distribution is also useful. The procedures you learn for using the left tail style normal distribution table apply directly to cumulative normal distribution areas found on calculators and in computer software packages such as Excel 2007 and Minitab. Use Table 5 of Appendix 2 in your book to find the described areas under the standard normal curve. So find the area under the standard normal curve to the left of z equals -1. First, shade the area to be found on the standard normal distribution curve as shown in figure 6.16. So in this figure, the area under the curve to the left of -1 is shaded in blue. Notice that the z-value we are using is negative. This means that we will look at the portion of Table 5 of Appendix 2 for which the z-values are negative. In the upper left corner of the table, we see the letter z. The column under z gives us the units value and tenths value for z. The other column headings indicate the hundredths value of z. Table entries give areas under the standard normal curve to the left of the listed z-values. To understand this, make sure while watching this video you are looking at Table 5 of Appendix 2 to see what we're talking about. To find the area to the left of z equals -1, we use the row headed by -1.0 and then move to the column headed by the hundredths position 0.00. This entry is shaded in this table, and we see that the area is 0.1587. So we're looking for z being -1.0 with a 0.00. So the intersection of those two is right here. Find the area to the left of z equals 1.18 as illustrated in this figure. In this case, we are looking for an area to the left of a positive z value, so we look in the portion of Table 5 that shows positive z values. Again, first we sketch the area to be found on a standard normal curve as shown in this figure. So look in row headed by 1.1 right here and move to the column headed by 0.08. The desired area is shaded. We see that the area to the left of 1.18 is 0.8810. Procedure: how to use a left tail style standard normal distribution table. For areas to the left of a specified z-value, use the table entry directly, just like we've been doing. For areas to the right of a specified z-value, look up the table entry for z and subtract the area from 1. Note, another way to find the same area is to use the symmetry of the normal curve and look up the table entry for -z. And 3, for areas between two z-values, z1 and z2, where z2 is greater than z1, subtract the table area for z1 from the table area for z2. So the first one, straightforward, just use the table. Second one, do 1 minus whatever the z-value is, if you're doing it to the right instead. But if you're doing between two values, you just do z2 minus z1. Convention for using Table 5 of Appendix 2. Treat any area to the left of a z value smaller than negative 3.49 as 0.000. Treat any area to the left of a z value greater than 3.49 as 1.000. Use Table 5 of Appendix 2 to find specified areas. Find the area between z equals 1 and z equals 2.7. So this one is between 2. So sketch the diagram, making what we want in blue. So it's not possible to see here, but this part is not in blue right here. That would still be in the same tannish color. Because we are finding the area between two z values, we subtract corresponding table entries. So like I said before, z2 minus z1. So the area to the left of 2.7 minus the area to the left of 1.00. So we get those two values, subtract them, and we get 0.1552. Find the area to the right of z equals 0.94. So sketch the area. The area to the right of 0.94 is the area under the entire curve, 1, minus the area to the left of 0.94, which according to the appendix is 0.8264, and we get 0.1736. Alternatively, the area to the right of 0.94 is equal to the area to the left of negative 0.94. Two different ways to do it. I prefer the first way. Alright, now time for the sponge. 3 questions, all pretty straightforward. You do want to use your book for these. Number 1, a normal distribution has mu equal to 10 and sigma equal to 2. A, find the z-score corresponding with x equals 12. B, find the raw score corresponding with z equals 1.5. Number 2, using a normal distribution table, find the area under the standard normal curve. A, to the left of z equals 1.17. B, to the right of z equals negative 1.23. And number 3, using a normal distribution table for a standard normal random variable z, find A, probability that z is greater than negative 1.69, or B, probability that p is between 0.05 and 0.8. Alright, that's it for the lesson. Once again, please make sure to take notes in the entire lesson, take a picture of everything, submit it all to Google Classroom, and have a good night.